So last time, I'm going to mute this actually for a sec. Holy, look at that thing. Wow. Let's mute this for a sec. What did we start talking about last time? What were we talking about on what day was that? Monday.
Probability distribution.
Absolutely, Haley. The idea of a probability, there we go. Distribution, beautiful. We're gonna kind of bring this idea to a conclusion today. Oh, I shouldn't say that. We're gonna stop the introduction to it today and build on it starting on Monday. But what was the big idea? What do you remember about what these things are, what they look like, what they contain? Anything you remember at all from Monday? And I know right now your brain's on project mode. You're like, I just got good. Very nice, Rach. You've got basically this two-column chart, one of which we usually call it X. And this was called the random variable. The random variable. What goes in that column? What goes in that column? The frequencies actually go in this column. Yeah, good, your data actually goes in this column. All the outcomes from your experiment go in this column. The frequencies, or in this case, relative frequency, what was this column called over here?
Probability.
Very nice, your probability of X, column. Good, I equated it to the F, that's what Rachel was talking about with the frequency column. I equated that to the frequencies column from before, but we turned them into probabilities because the mathematics is actually much easier to deal with when you have a probability of X column than when you have a frequency of X. And we'll see more of that today. I have three distributions I'm going to play with today. One of which involves rolling two dice. We're going to reanalyze what you guys collected on Monday. The second involves a gambling application, and the third involves life insurance, which, believe it or not, is exactly the same as a gambling application. I mean, it, as far as from the actuary's point of view of those making the insurance rates on the policies, there's no difference at all. It's basically how much does the house want to pay out if you hit the jackpot, quote unquote. And we're talking about life insurance, hit the jackpot is dying. Because for the actuarial, for the life insurance company, that's when they have to pay out. Like Vegas, when the house has to pay out. So it's all related back to this idea. So you've got a series of outcomes listed out here, and you've got the series of probabilities listed out here. Fair enough? That's the big idea. And the one we started with, the first example we started with last time was the rolling a single die example. Rolling a single die. So example number one was roll a single die. Okay? So X was the number of pips that you see. And this was a fairly boring distribution, wasn't it? Fairly boring. What were the outcomes? Number of pips you could get rolling a single die. Perfect. 1, 2, 3, 4, 5, 6. Beautiful. 5, 6. And how about the probabilities of all these things? Absolutely. You had a 6, all of them were 1/6 because they all happened 1/6 at the time. 1/6, 1/6, 1/6. Beautiful. And then one of the last things we did, I believe, was I asked you, on average, I know, thrilling. It's a good yawn. On average, what do you roll when you roll a single die? It was the last computation we did, it was 3.5. And if you remember what we drew a beautiful analogy between averaging this and averaging the old school weighted mean t-tables, where you did x times f times x times, or plus x times f plus x times f. We worked through it, it was beautiful, beautiful work. We're going to stop working through it in that way because that tends to get kind of tedious and time consuming and there's much more efficient ways. But more importantly, why is the average 3.5? You can't roll 3.5. You can roll a 1, a 2, a 3, a 4, a 5, and a 6. So where does this average of 3.5, like conversationally, where does that come from, friends? How do you explain a 3.5? If you can't actually roll a 3.5, how do you explain an average of 3.5? What do you think? Give me some ideas. Oh, go ahead.
It means that on average, over time, it was
okay, good.
On average, over time, this is the population.
Yeah.
So
notice I'm calling it mu. Very nice. It's mu.
Of
Good.
the population. So it means that on average, every person will have at least 3.5 chances to get 3.
You're close. You're damn close. It's not a chance. What I'm saying is,
Oh,
this is the
dice.
the
Okay.
average number of pips. And you said it beautifully before. This is your data column, and the average is the average of your data column.
Okay,
You
so-
said it perfectly.
So on average over time, each one of the population will throw the dice and it will get between 3 and 4.
Oh, that's well said.
Yeah.
That's well said. Actually, that's very well said. Between 3 and 4, which becomes 3.5. You can look at this average from a median point of view, but I'd rather look at it from a pure average point of view, from the mean point of view. How is this related to the lollipops?
It's because it's like distributed or whatever.
Right. For every 6 that gets rolled, what else gets rolled somewhere down the line? A 1. And the 1 and the 6 average to a 3.5. There are 7 total pips for 2 people. And for every 5 that gets rolled, a 2 gets rolled. So there are 7 total pips for those 2 people. And for every 4 that gets rolled, you said this one yourself, well, it was perfect. For every 4, a 3. Those 7 pips get distributed among 2 people. So for every x, there is a 7 minus x, if you don't think of it algebraically, that gets rolled somewhere. And the 7 minus x and the x combine to make 7, divided by the 2 people, it's going to be 3.5. Is that a fair assessment? Just like lollipops. The folks up here, somebody had 6, somebody had none. The person that had 6 gave 3 of theirs to the person that had none. And then you had 6 lollipops among 2 people, which means 3 among 1 person. That's all you're looking at.
We can count also outliers, right?
Good, very nice. Thank you, Elena, thank you. There's a third way of measuring outliers. There is a third way of measuring outliers that ties to distributions. Would you call any of these outcomes outliers? What do you think? Would you call any of these outcomes outliers?
No. There's no,
Which method are you? Oh, go ahead, Jada.
well, there's no like higher chance for one of them to be rolled.
Did you hear what Jada just said? She's bridging the gap between the old way we talked about outliers and the new way. So check this out, check this out. When you talk about outliers from a probability point of view, it's different in most times than dealing with a statistical outlook. A statistical outlook, you have to create a standard deviation, which I don't want you to have to crunch these standard deviations by hand. And you'll see why momentarily when we get the 2 dice. It just gets messy. You have to create a standard deviation and then do 2 of those around the mean. But I wouldn't do that for this. Why? What is this data not? If you took a picture of it, if you took a picture of this is the number of pips. 1, 2, 3, 4, 5, 6. And I put the probability. I want to go with probability still. And if I drew a histogram of this data, it's going to look exactly, Elena. It's going to look like this. It's going to look like this. So what's that not? It's not bell-shaped. So therefore, I can't use the 2 standard deviations rule, which means we're going to have to rely on the quartile range rule. And we can fall back on that or not, but I love what Jada said. What did you just say? There's no one event that happens.
Oh, like more.
Good!
Than the other one.
There's no one event that happens more frequently than some other one. If one's an outlier, for example, that means they all have to be outliers because they all happen 1/6 at a time. Well, that means the entire data set's an outlier. Okay, that's kind of hard to fathom, right? You can't have everything be an outlier. Everything can't be different than average or typical. Good, very nice, Jada. Hold that thought, my friend. Hold that thought. Hold that thought. What I want to do now is I want to take this beautiful, guys, by the way, that was a beautiful explanation of everything, every piece of this distribution. What I want to do now is, before we go back to your data, I want to look at, and to see if we can come up with this. I call this, if you will, like the classical probability distribution for rolling a die versus the data distribution for rolling a die. If you remember yesterday, we graphed both of them. We graphed the actual distribution you guys got from your data from a single die, and then we graphed the perfect distribution, which is the perfect horizontal line, and Jada made an awesome connection between if you cut the tops, they fit in the bottoms. It was beautiful. What I want to do is I want to turn things around this time. I want to start by looking at the perfect distribution of rolling 2 dice. So let's come over here, and then we're going to come back to your actual data. We're going to come back to your actual data. So experiment number 2. Experiment number 2. Let's roll a pair of dice. And I wasn't going to do this until I realized, I'm like, oh, you guys just got done this project. I bet you this idea is fresh in your mind from your projects. We can exploit that right here. Okay, so what am I interested in now? I still want to make my random variable table, xp of x. I still want to make this. I still want to make this. But what's this x? I should probably make this over here. what's this, what data am I interested in now if I'm rolling a pair of dice? So doubles implies what, Robin? Tell me more about this.
Rolling the same numbers.
I could be interested in, especially playing craps, right?
Yeah.
Because rolling double ones is a bad thing. But rolling double fours later on might be a good thing. If you bet 8 the hard way, you actually get more money than just getting an 8 in general.
Wouldn't it be like 2, 3, 4, 5?
Exactly, which would be the, I'm just trying to put like an English name on this. You got it, Jada. What I asked you guys to collect yesterday was the sum of the 2 dice, right?
Yeah.
The 2 dice is pips. It's time for a new one on this thing. Mushroom. That's what we're interested in. And you got it, Jada. The smallest sum, as Robin pointed out, is snake eyes, which is 2. And then you've got 3 and 4 and 5 and 6 and so forth. 7, 8, 9, 10, 11, and 12. Beautiful. Now what I want to try to do right now is I want to try to come up with these probabilities without using your raw data as a starter. I'm not saying that that's a bad thing. I'm saying it's a great thing. But since you're fresh off this last project, I want to see if we can tie in. For example, what is the chance of getting snake eyes if you throw a pair of dice? What is that? Let's make a little side. Go over here. Go over that sideboard. Make a little worksheet. All right. What's the chance of getting snake eyes? I hear 1 out of 11. I hear 1 in 36. Love it. Love it. Now there are 11 outcomes from 2 to 12. There's 11 things there. But if we say it's 1 out of 11, what does that make? What assumption does that make about all the outcomes? What does that, Jen, what do you think?
That it'd be only one die.
Good! That distribution of a single die, I gave it a name yesterday, a uniform distribution. That means every probability is the same as every other probability. And that happens sometimes. With a single die, with a single coin, things like that are uniform. This is not. Because if we said the chance of getting snake eyes was 1 in 11, that would mean the chance of rolling a 3 would be 1 in 11. And that would mean the chance that rolling a 4 is 1 in 11, which means every sum is just as likely as every other sum. Did we notice that on Monday? Weren't some sums coming up more often than others? Which ones in particular? Do you remember? You might not remember, and it's okay if you don't. We'll go back to your data. Actually, what the hell, let's look at your data right now. Did you notice the sums that were happening more frequently on Monday? Turn this back on. I still have your data in here. Stat edit. Okay, you guys are in L5 and L6. There you guys go right there. Pull this down. So we got 9 snake eyes, 12 threes, 26 fours, 38 fives, 46, 49, 54, 8s, and then we got 42 9s, 33 10s, 20 11s, and 13 12s. Interesting. What are you seeing, Jada?
Like goes up the middle numbers.
Mm-hmm. So the ones at the end are kind of hard to get, and then it gets up towards the middle. So starting from smallest to largest, kind of unlikely, rises to likely, falls off to unlikely. Good, good. And that's, like I said, that's just your guys' experimental empirical data. Let's go back to the actual snake eye analysis over here and take a look at this. All right. So first of all, in order to figure this out, we really should figure out what the sample space is. Right? We should figure out how many ways you can roll a pair of dice. With a single die, it's easy. 6. You throw a die, it's got 6 outcomes. What if you throw 2 dice? Think project you just turned in. How many ways can a pair of dice fall? Think about the very first page of that project. What do you think? Say, go ahead.
12 in the second power?
Why 12?
Oh,
Why 12?
because...
I'm hearing second power. Why second power, first of all? I like that very much.
I mean, yeah, because there are 2 dice.
Because there are 2 dice, so
But
you're rolling the first
then-
one and then rolling the second one. Something needs to be squared.
Yeah.
Good. Nini, what are you thinking? Why 144? Then that's 12 squared, right?
Yeah.
Now my question is, where did the 12 come from?
Yes, 12 by 12, 120, 40.
But that would imply the dice have 12 sides each.
Sorry.
They only have 6 sides each, so it's, right, but 6 sides on the first die, and 6 sides on the second die. And what does the word "and" mean in our class? And, Multiply, or means add. So, if there are 6 possibilities for the first die, and 6 possibilities for the second, putting them together gives us 6 times 6, or 36 possibilities. That's your sample space. When you throw a pair of dice, there are 36 possibilities for that pair of dice. Hey, you know what? I guarantee we can find a Google image of this. I guarantee it. I guarantee it. Somebody tell me, see how good I am. Computer, blank screen. Why am I not seeing anything?
One chance.
Oh, there we go.
I think we have one day off.
2 dice outcomes.
I think so.
Hot damn. I like this one a whole lot right here. Can I make that one bigger? Oh, yes. I like that. Zoom it. Let me make it. There they are, friends. Those are your outcomes right there. Those are your 36 outcomes. Your first die across the top, the green one, if you will. The second die down the side, the red one, if you will. And matching up every possibility for the green one with every possibility for the red one gives you 36 possibilities. Now take a look at that stuff. Now realize, for our old distribution here, it was just simply looking at that. Or red, not one or the other, not both. But then you add a second die, and you have to have a second dimension. If we had a third die, you have to have a branch coming out like this, and you'd have 216 possibilities. We won't get to that right now. Let's play back with this one. So take a look at that, friends. What's the chance of rolling snake eyes?
1 out of 36.
1 out of that 36. It's right there. There's the only one, right? The only chance of snake eyes is 1 out of that 36. What's the chance of rolling a sum of 3? What's the chance of rolling a sum of 3? So how many ways can you get a sum of 3?
2.
You can get it right there, or you can get it right there. Do you see how there's 2 different possibilities? There's 2, because in this one, the 2 is green and the red is the 1 is red, and in this one it's backwards. The 2 is red and the 1 is green. That's actually 2 outcomes. That doesn't happen for snake eyes, because if you switch the 1 and the 1, it's still the same 2, 1, and 1. You don't have to turn the dice at all to change it. So there's 1 way out of 36 for snake eyes, 2 ways for a sum of 3. How about for a sum of 4? There's 3 for a sum of 4. How about for a sum of 5? Sum of 5? 6? 7? And look what's predictably going to happen. Here's your 8. Just 5. 9. 10. 11. And 12. So just like you guys said was going to happen, it starts rare, gets more likely, and then falls off to rare again. So I think we can fill in our distribution now. I think we can fill our distribution in. The chance of a 2 is 1 in 36. The chance of a 3 is 2 in 36, and so forth. 3 in 36, 4 in 36, and so forth, and so on. 5 in 36, 6 in 36, and then it starts going back down again. 4 in 36, 3 in 36, 2 in 36, and 1 in 36. Does our data look kind of like that? It does. Our data kind of looks like that. It started small, went up. Do you remember where our most frequent outcome was, though? Our most frequent outcome was not at 7. It was actually at 8. It was actually 8, but that's experimental error. That's going to happen. That is going to happen when you have this kind of situation. When you have a small data set, you're going to have that random clumping in different places, but it's close to where the true center is at 7. So here's the first thing I want you guys to do. I want you to use your TIs to find the average roll, or the average sum for this distribution, which you probably already know what it is. And I also want you to find the standard deviation around that sum for this distribution. Right? Notice, both of these will be given to you when you run one of our stats. And while you're getting this guy entered into your TI, you're going to do L1 and L2, just like yesterday. Then run your one-bar stats. I'm going to simulate the experiment like we did yesterday using Excel up on the front board here. Thank you. dsearles.org for the image. That was wonderful.
And then